So, welcome everyone to the May 2025 eCHT mini course. Today we have Nat Stapleton, who will be giving the first lecture on a series on power operations and global algebra.
Okay, let's get started. Thank you all for coming. It's great to see 30 people here, which is a full classroom. Um, the goal of this course is to introduce you to global algebra and talk about some modern themes, some things that I've been working on towards the end, entirely through examples. Um, we're going to talk about several examples of objects in global algebra. And I've also tried to make this as inclusive as possible. So we're going to start in a place that I hope everyone feels comfortable, but I promise to move fast enough to get to uh, deeper things reasonably quickly. Also, my dog Griff is here, and he may have needs at any time that I have to take care of so that he stops whining in my face. So just so you know, you may hear him. Um, uh, okay, let's jump into it. So the course is called Power Operations and Global Algebra, and hopefully I'll be able to make these notes available afterwards. Okay, that is a terrible line. Let's do better. There we go. And I want to begin with some context that I find helpful. It may be unfamiliar to you, and so you won't find it helpful, but don't worry about it. We'll build stuff up from the beginning in just a moment. But there's a cohomology theory that's one of the most important cohomology theories in algebraic topology, which is called complex K theory. And that's going to be our starting point. So I'll write KU down here. And the chromatic perspective says that a good thing to do is complete KU at a prime P. And so there's a map over here to the completion of KU at a prime P. And when we do that, we actually get something called a height 1 Morava E theory. So this whole line down here is at height 1. And after I complete K theory at a prime P, it turns out there's lots of generalizations that see deeper and deeper into spaces, groups, the stable homotopy category. And these are called the Morava E theories. So there's the first one right here, that's E1, but I can keep going. There's an E2 and an E3, and it keeps on going up until you get the whole way to infinity. And up at infinity is singular cohomology with coefficients in FP. And mapping to all of these things is the sphere spectrum. These are all E infinity ring spectra, and the sphere maps to everything. Uh, and all of these things admit global equivariant versions. On the left-hand side here, these are kind of fancy global equivariant versions. But on the right-hand side, the right notion of global equivariant is just Borel equivariant. And so out of this picture, we can ask for the values of these cohomology theories on finite groups. So we can take the values on finite groups taken appropriately. And when we do that, this gives rise to objects in global algebra, whatever that means. But this picture that's here gives an overview of what we're going to be doing in the next 5 lectures so that you know what's coming up. So when I consider complex K theory on a finite group, we get the representation ring, and we're going to spend 2 lectures on the representation ring. So down in this corner, kind of getting a feel for what's going on. And then we're going to spend 1 lecture up here. The equivariant version of the sphere spectrum gives rise to Burnside rings. So we're going to spend an hour on Burnside rings. And then we're going to spend an hour on the Morava E theories. and try and understand what those see about finite groups and the objects in global algebra that arise. And we will not have a lecture on singular cohomology or the cohomology of finite groups. It would be nice to, but there is not time. Instead, our fifth lecture will be about some objects in global algebra that have shown up in my recent work with my students, um, called partition functors, which are objects that capture the behavior of power operations. So that's like the context for what's going on. You didn't need to understand much about that. Let's start with the basics and talk about the complex representation ring. So we're going to start in this bottom left corner. So this next section is called the complex representation ring. And we're going to begin with the basics. So let's recall how this goes. So first of all, a G representation, which I'll just call G rep. G is a finite group, is a finite dimensional complex vector space, V, with an action of G through linear maps. And this is equivalent to several other kinds of data, so it can be repackaged in several ways. So first of all, it's a group homomorphism from G to the automorphism group of V, which if I choose a basis, is isomorphic to GLN where N is the dimension of V. And it's also equivalent to the data of a finite dimensional module over the group ring of G. Right, finite dimensional. And this group ring is a non-necessarily commutative ring, but this is another way to package the data of a G representation. And a map of G representations is just an equivariant linear map. So a linear map between the vector spaces that interacts appropriately with the G action. There's a direct sum of G representations that we just extend the G actions linearly. And there's also a tensor product of G representations. That's a little bit more interesting, so I'm going to say something about it. So the tensor product might not work the way that you think. So what you do is you tensor over C. So you take V tensor over C with W. You don't tensor over C bracket G. That's the wrong thing in this case. So this is the tensor product of G representations, and G acts diagonally on the tensor factors. And what I want to do to build the representation ring of G is to consider isomorphism classes of G representations. So let's let square brackets V be the isomorphism class of V. And then the set of isomorphism classes of G representations carries a bunch of extra algebraic structure. So we can define a sum of isomorphism classes of G representations. This is the isomorphism class of the direct sum of the G representations, and we can define a product of G representations. The product is the isomorphism class of the tensor product. And each of these operations has an associated identity. So the additive identity 0 is the isomorphism class of the zero-dimensional complex G representation. And the multiplicative identity 1 is the isomorphism class of the one-dimensional G representation with trivial G action. And this nearly gives us the structure of a commutative ring on the set of isomorphism classes of G representations. The only way we've failed to get a commutative ring structure is that we don't have additive inverses. But this can be repaired in a very natural way using the Grothendieck ring construction. So we'll let Ru of G be the Grothendieck ring of isomorphism classes of G representations under this sum and product with this sum and product. Uh, and so this is a definition of the representation ring, but maybe it doesn't tell you how to think about it. And so that's our next goal, to discuss how to think about it. One important definition is the definition of an irreducible G representation. So a G representation is called irreducible if it has no proper non-zero sub-representations. And there's an important theorem about irreducible G representations that is kind of the thing that makes all of this work, which is called Schur's lemma. And I just want to recall it. This is a good exercise. If you haven't seen this one before, it's a good exercise to try and prove it. It's just a linear algebra exercise. And it says that if V and W are irreducible G reps, then, well, one of two things happens. If V is not isomorphic to W, and I have some map F from V to W of G representations, well, then F is zero. F is the zero map. And if V is isomorphic to W, then any map F from V to W is just multiplication by a scalar. And this result gives a lot of control over G representations and the representation ring. So I just want to talk about two applications of this. So the first one is to representations of abelian groups. So this is an example. Haven't had a lot of examples so far. So let's assume that A is an abelian group, and V is an irreducible A representation. Then for A and A, we can consider the action map. So the way that little a acts on V gives us some linear map from V to V, but because A is abelian, this is a map of A representations. And now Schur's lemma tells us that if I act on some vector in V by little a, this must, for all V, this must be multiplication by some scalar. So for some C in the complex numbers. But that means that the subspace generated by little v is a subrepresentation of V, which implies, since V was irreducible, that it's everything. So the dimension of V must be 1. So that's one nice application of Schur's lemma. irreducible representations of abelian groups are always one-dimensional. Another application is to the representation ring itself. So every G representation is a sum of irreducibles in a unique way. Okay. As usual, up to isomorphism and permutation. But the uniqueness here, this is Schur's lemma in action again. This is Schur's lemma. It's a good exercise. And so what's that mean? That means a lot for the representation ring. So RU of G is additively, whoa, terrible, is additively a free Z module or a free abelian group with a canonical basis given by the set of isomorphism classes of irreducible G reps. Isoclasses. So that tells us the entire additive structure of the representation ring of G, and that it's not particularly interesting. The reason people must care about these must have something to do with the multiplicative structure, uh, which is of course more interesting. If I tensor together two irreducible G representations, well, I need to know something about how that decomposes as a sum of irreducibles. So let's look at some examples of these representation rings. So let's start with the easiest example. So the easiest example is the representation ring of the trivial group, which I'm going to denote with an E. An E representation is just a finite dimensional vector space. These are classified up to isomorphism by their dimension. So there's a natural number worth of those, and when I throw in additive inverses, I get the integers, and I really do get the integers. That is how dimension works with direct sum and tensor product. So I really do get the integers on the nose. Let's go up to the next harder one, which is the representation ring of a cyclic group. So I'm going to denote a cyclic group by C sub n, often thinking about it as a subgroup of S1 and thinking about S1 as a subgroup of the complex numbers. So C sub n acts on the complex numbers by rotation. Rotation by 2 pi I over n, also known as multiplication by e to the 2 pi I over n. And let's call this rho. And then I can tensor rho with itself. So this gives us an action, which I'll call rho tensor rho on C tensor over C with C, which is just another copy of C. Since this is acting by multiplication by something, once I take the tensor square, it's multiplying by the square, which is rotation by 4 pi I over n. And we can continue in this way, taking tensor powers of rho. And this will end once we rotate by 2 pi I, which is the identity. So that's the nth power. So rho tensor n is the trivial action. And it turns out it's not a hard exercise. It's really not a hard exercise. It's worth doing if you haven't done it before to check that all the powers up to n are non-isomorphic irreducible representations of Cn. So, and these powers are all non-isomorphic. Whoa, non-isomorphic. So if we set X to be the isomorphism class of rho, then we learn that we have a presentation for the representation ring of Cn. It's isomorphic to Z adjoin X mod X to the n minus 1. It's not important for the purposes of this talk, but if you know what the multiplicative group scheme is, it is a nice observation that this is exactly the n torsion in Gn, the multiplicative group scheme. That is often quite useful. There is a special element in the representation ring of Cn. There's a thing called the regular representation. So I can take the free complex vector space on the underlying set of Cn, and Cn acts on this. This is called a permutation representation. And in this case, it's called the regular representation because it's G acting on the free complex vector space on G. And let me write that down. So this is the regular representation. And it's another good exercise to help you understand what RU of Cn is, to see that the isomorphism class of this Cn representation is the element 1 plus x squared up to x to the n minus 1. So that's who that is inside of the representation ring of Cn. Okay, are there any questions at this point? We've discussed a definition, we've done some examples, we've got Schur's lemma. I want to jump into restrictions and transfers, but I know that there are some people who are younger graduate students in the audience, so you should feel free to ask questions at this point. Okay. So that was our background section. So let's talk about restrictions and transfers. So we're working our way towards understanding what global algebra is. Um, so we don't just want to understand these representation rings alone, like just for a single group. The idea of global algebra is to understand how these things fit together as the group varies. And that's what we're going to jump into. So let's assume that I have some group homomorphism F from H to G. And it does not need to be injective. It's just an arbitrary group homomorphism. Then the restriction along F is a map from the representation ring of G to the representation ring of H. And this is a ring map. And where does it come from? Well, it's induced by restriction. If I have a G representation V, well, I can pre-compose with F to get an H representation. So I've got H mapping via F to G. G acts on V, so H acts on V through F. And this gives us an H representation from a G representation, and this behaves well with direct sum and tensor product and 0 and 1. So this is a ring map. That is the easiest of all of our structure maps. The next one is the transfer. Doing this. There we go. So the transfer along F is a map from RU of H to RU of G. This one is not a ring map in general. This is an additive map. And how is this one defined? Well, this is induced by the map taking an H representation V to the base change of V to C bracket G. So I can form the base change C bracket G tensor over C bracket H with V. And this base change comes with a natural action of G. And so this gives us a G representation. And this kind of base change interacts well with direct sums, which is why this is an additive map. But it does not interact as well with tensor products. We'll say more about that in a little bit. It is important to note that these transfers make sense for an arbitrary map of finite groups. This is actually a little bit unusual. The case of an injection, where F is an injection, is the case that's important for the definition of a global Mackey functor, which we'll discuss a little bit more in a bit. But let's do an example. So let's take the inclusion of the trivial group into G. We'll call this I. Then the restriction along I is a map from RU of G to RU of E, otherwise known as Z. So this must produce an integer from a G representation. But what am I doing? I'm just taking the underlying vector space. So this map must take a G representation V to the dimension of V. This is also called the augmentation map for the representation ring of G. So this is a ring map that we have. It's the dimension map, takes a G representation to its dimension. Now the transfer is pretty interesting already. So this goes from RU of E, otherwise known as Z, to RU of G. This takes 1 in here, which is the isomorphism class of the complex numbers, and does this base change, and this produces the representation, which is the regular representation of G. So the free complex vector space on the underlying set of G with G action given induced by the G action on little g on G. So we get the regular representation out from this transfer. Oh yeah, there's one other example that I want to do. What if I have a surjection? Now this is a good exercise. So if I take the transfer along F of some H representation V, what you get here is the isomorphism class of the G representation, that's V mod the kernel of F. So a transfer along a surjection is taking the quotient by the action of the kernel. And that's a good one to think about. Okay. Um, so uh, so given a group homomorphism, we have these two maps, and they're going to interact in some way, and they interact in a particularly interesting way. And so I want to talk about two ways that these maps interact with each other. So these interact in two important ways. And these are going to introduce us to the definition of a global Mackey functor and a global Green functor. So the first one is the double coset formula. So this says the following. So if I've got two subgroups, H and K, contained in G, then I can express the composite where I take the transfer from H to G, and then I restrict from G to K in terms of restrictions followed by transfers. So it lets us shuffle these things around. So the formula is a little bit annoying. Most people will prefer not to write it down, but I think I'll do it one time here. So this is the sum over KSH, the double cosets of K and H in G, of the transfer along K intersect SH S inverse sitting inside of K. There's a secret conjugation by little s, and then restriction along S inverse KS intersect H sitting inside of H. So you sum over these double cosets, and then the data of the double coset allows you to write a restriction followed by a transfer using these intersections. And there's a conjugation moving one of the intersections over to a conjugate intersection. Okay. Um, and uh, and and this now I've told you the definition of a global Mackey functor. So a global Mackey functor is a way of associating abelian groups to finite groups so that you have restriction maps, you have transfer maps along injections, and the resulting restriction and the restriction and transfer maps satisfy the double coset formula, which I've written here. So that's the definition of a global Mackey functor. But by doing this example, I can also tell you the definition of a global green functor using the second way that these two maps interact with each other, which is called Frobenius reciprocity.
Nat, can I ask a question real quick?
Yeah,
So you mentioned that uh, in this case of representations, we have transfer for all group homomorphisms.
yeah,
But now you're saying that for global Mackey functor, we only require transfers along injective homomorphisms. Is that
that's
correct?
correct. That is the
Okay.
definition. Yes. Yes, it's too much to ask of the world to have transfers along all homomorphisms, but it happens to be the case for representation rings that you have this. Yeah. But if I take some arbitrary cohomology theory E, and I consider the functor that takes G to the E not cohomology, like E0 cohomology of BG, this in general will not have transfers along arbitrary maps of finite groups because those don't correspond to finite covers.
Thanks.
And we want those to be examples of global Mackey functors. It's very important that those are examples of global Mackey functors. Yeah. So what's Frobenius reciprocity? Well, Frobenius reciprocity tells us that the transfer is actually a module map. The transfer up here from RU of H to RU of G is an RU of G module map. But what's the RU of G module structure on RU of H? Well, it's the one induced by restriction along F. So in symbols, this says that if I've got X in RU of G and Y in RU of H, it keeps thinking I'm double tapping this pen. Um, then the transfer along F of the product of the restriction of X with Y is X times the transfer along F of Y. And that just says that it's a map of RU of G modules. But this has a nice implication. It implies that the image of the transfer along F is an ideal in RU of G, because it must be an RU of G submodule. Um, and uh, and with this in hand, I can tell you what a global green functor is. So a global green functor is a functor from finite groups to commutative rings, so that the restriction maps are ring maps, just like this one, transfers along injections still, satisfying the double coset formula and Frobenius reciprocity. So this tells us what a global green functor is. Okay, I want to do a more involved example with restrictions and transfers. Using the fact that we have calculated things about representation rings on cyclic groups already pretty completely. So, okay, so let's do an example. So let's assume that I have some natural number n, which is k times d, so that I can consider the short exact sequence c sub k sitting in c sub n and mapping to c sub n mod c sub k, which is isomorphic to c sub d. Then I want to consider restrictions and transfers along these maps and see how these things fit together. So let's start with the restriction along F. This is kind of the easy one. So this is a map from RU of Cn to RU of Ck. We've given descriptions of both of these things. So this is isomorphic to Z adjoin X mod X to the n minus 1. And this is isomorphic to Z adjoin X mod X to the K minus 1. Where X is just the action by rotation on the left by E by 2 pi I over N, and on the right by 2 pi I over K. So these X's are different X's. They're different X's. But when I restrict the action that rotates by 2 pi I over N to C sub K sitting inside of C sub N, I get the rotation by 2 pi I over K. So this map sends X to X, which is a perfectly good ring map, well, under the condition that K divides N. And it's a surjective map. So this is surjective. So this is a surjective ring map. Let's consider the transfer along F. So this is a map from RU of C sub K to RU of C sub N. But because that restriction map was surjective, this map is determined by where 1 goes and Frobenius reciprocity. So this is determined by where 1, otherwise known as C to the 1, goes. Because the restriction along F is surjective. Now, this is an often useful observation that if your restriction map is surjective, then you can completely understand the transfer map with one piece of data. I have found this useful in real work. So where's 1 go? Well, 1 goes to the base change, which is C bracket Cn tensor over C bracket Ck with C. And this is the Cn representation. That's the free complex vector space on Cn mod Ck, where Cn acts through the quotient. It acts on this set through the quotient map from Cn to Cn mod Ck. That's what you get. You're killing off the Ck bit. when you do this. And that was all we needed to know. But we've still got G. And so let's see what's going on with the restriction on G along G. So this is a map from RU of CD to RU of CN. And now I'm taking this quotient, right? So Cn is acting on the complex numbers when I restrict. Okay, so I've got the CD action by rotation by 2 pi I over d, and I'm restricting along this quotient, but that's exactly telling me that x here, well, what am I going to get? I'm going to get the rho for Cn to the kth power. So x here goes to x to the k. And that is a perfectly good ring map. But because it allows us to figure out who this representation is inside of RU of Cn, because another representation that I could restrict here is C on CD. So that regular representation of C sub D must restrict to C on Cn mod Ck, because that's how Cn acts on CD. And we've already calculated that the regular representation of CD corresponds to the sum 1 plus x squared up to x to the d minus 1. And so now we know who the isomorphism class of this representation is. In RU of Cn, it is 1 plus x to the k plus x to the 2k all the way up to x to the d minus 1 times k. So that's who that representation is in this presentation of the representation ring of Cn. So by messing around with this example, not only did we hopefully get a feel for what the restriction and transfer maps are doing a little bit more, but we also were able to figure out some more permutation representations were inside of the representation ring of Cn. Okay, does this example make sense? I kind of got the whole thing on the screen here. Okay. I want to do one more example just because we should do a surjection. So I could take the transfer just along C2 to the trivial group, which goes from RU of C2 to RU of E, which is Z. And here I've got 1, and I've got X. And what we're doing when we take a transfer along a surjection is taking the quotient by the kernel, which in this case is all of C2. But C2 acts trivially on 1, so the quotient does nothing. So 1 goes to 1. But C2 acts by the sign representation on X, and that's a non-trivial action on the complex numbers. So when I take the quotient in vector spaces, I just get a zero-dimensional vector space. And so that's what that transfer map is doing, and you could generalize that. These restriction maps let us begin to understand the representation ring of a product. So here's kind of a general thing you could do with a global green functor, but something special happens in the case of the representation ring. And I'll call this mini section, which is very small, the Kunath isomorphism. So I could consider the projections. If I have two groups, G1 and G2, I can consider the projections from G1 times G2 to G1 or G2. I'll write GI, pi I. And I can restrict along these projections. So the restriction gives rise gives a map. Well, I get a map from RU of G1 to RU of G1 times G2. And I also get a map of RU of G2 to RU of G1 times G2. So I get a map from the pushout of these two, which is the tensor product, because these are maps of commutative rings. So I get a map from RU of G1 tensor RU of G2 to RU of G1 times G2. So far, I haven't said anything that's not true for any global green functor. But there's a theorem in this situation, which is that this map is an isomorphism. So here's a fact. So this is an iso for representation rings. In general, there's absolutely no reason to imagine that such a thing is an isomorphism. But for representation rings, it always works. There's this map that you always have is in fact an isomorphism. Okay, great. We good? I have more people than when I started. Okay, that's amazing. I was assuming I'd lost like 5 people by now. Okay. We were able to give a presentation of the representation ring of a cyclic group. Because we have this Kunith isomorphism, you could now give me a presentation of the representation ring of any finite abelian group, right? But in general, we don't understand representation rings of finite groups by giving presentations for them. This is sort of an awkward way to understand representation rings of finite groups. Instead, we understand these representation rings through character theory. That is the tool we have to understand representation rings. And that's the next big section, which is another structure carried by the representation ring, which is not part of one of the axioms for a global Mackey functor or a global green functor or any of the other global functors that I'm going to talk about, but is a really important structure carried by all of the things that I'm going to talk about. Okay, so here's how this goes. I have lots of, well, we're going to go with the classical route on this. So let's let G mod conj be the set of conjugacy classes of elements in G. And let's let Q adjoin mu infinity be Q adjoin all roots of unity. So the rationals adjoin all roots of unity. Then if I have a representation rho, which now I want to think about as a group homomorphism from G to GLN C, G representation, then I can consider for each G and G, I can consider the trace, which I'm going to write lowercase, of rho of G. This is trace, not transfer. And this is some number in the complex numbers a priori. But as rho of G can be put in Jordan normal form, and that doesn't change the trace because it's conjugation invariant. And since G has finite order, once I've got rho of G in Jordan normal form, there's just roots of unity along the diagonal. And so the oh my gosh, to change the setting. So the trace of rho of G is a sum of roots of unity. And further, since uh, again, conjugation invariance, so HG H inverse is the trace of rho of G, we get a map from RU of G to a ring that I'm going to call, well, let's write it this way, to the ring of functions on the conjugacy classes of elements inside of G taking values in Q adjoin mu infinity. G is finite. And the name for this ring is class functions. Um, and so this gives us a map from RU of G to a very simple ring. This is, as a ring, this is just the product over G mod conj of Q adjoin mu infinity. And it turns out that this, so here's just another, I'm going to hit us with another fact. So I'm going to call this map chi. Chi is an injective ring map. And even much more is true. And it induces an isomorphism between the base change. Oh, yeah, we're only thinking about finite groups. Yeah. And induces an iso between the base change of RU of G over Z with Q adjoin mu infinity and CLG, Q adjoin mu infinity. This tells us, this process gives us a ring map from RU of G, which is a commutative ring that's kind of hard to understand because I need to understand something about the way that tensor products of irreducibles decompose into sums of irreducibles. And a very simple ring, which is just a product of Q adjoin mu infinities of fields, a product of fields. And this map is an injective ring map, so RU of G actually sits inside of this product. And after I do this base change, I get the product. So the failure of RU of G to be a product is exactly rationalizing and adjoining some roots of unity. So this is like probably like for arbitrary G, our best tool for understanding representation rings of G. But this isn't actually the complete story on this. Even more is true. And this even more lets us not just understand the base change of RU of G to Q adjoin mu infinity, but just the rationalization of RU of G. So let's let Z hat be the profinite integers. So this is the inverse limit along the divisibility diagram of Z mod n. So this is a subring of a topological subring of the product of Z mod n's with the product topology. That's how you think about inverse. Well, that's a way to think about inverse limits. So this is the profinite integers. And if you haven't seen them before, you should think about them as not actually too different from the integers, but they have way more units than the integers have. So this is kind of the important feature of the profinite integers. They have way more units. So why are these coming up? These are coming up because the Galois group of Q adjoin mu infinity over Q is the profinite integers, is the units in the profinite integers, also known as the automorphism group of Z hat. And G mod conj also has a weird description in terms of the profinite integers. I could say that G mod conj is the set of continuous maps from Z hat into G mod conj, where G acts on this by conjugation of continuous maps. And this shows me that the automorphism group of Z hat, which is Z hat times, acts on this by precomposition. It acts on this by precomposition. This is a very complicated way of saying that if I have a number that's relatively prime to the order of G and I have an element in G, I can raise it to that power. And that's all that this action is doing. And when I raise to those kinds of powers, I'm sort of getting an automorphism of G mod conj. Okay, what does this have to do with the story? Well, this Z hat times action graduates to an action on class functions taking values in Q adjoin mu infinity. So there's Z hat times acts on these class functions via a conjugation action where I put together the action of Z hat times on G mod conj and the action of Z hat times on Q adjoin mu infinity, since it's the Galois group. So that gives us an action here. And this character map lands in the fixed points for this action. And is equivariant for the Z hat times action, where on the left-hand side, I just act on Q adjoin mu infinity. And so since it's equivariant, I can hit the left-hand side here with fixed points as well. But since it's the Galois group, I just get Q. And it was this map up here was an isomorphism. So what we learn is that the rationalization of the representation ring of G is isomorphic to the Z hat times fixed points, or Z hat times invariance in Q adjoin mu infinity valued class functions on G. All right, what I want to do next is some examples, including a very important example involving representation rings of symmetric groups, but I see based on time that that's going to have to wait for next time. So we'll finish up character theory, talk about its relationship to restrictions and transfers, and then jump into power operations next time. So that's the end for today.
All right, great. Let's thank Nat for the first lecture.